speaker this session, Dr. Yasushi Ikeda from Kyoto University of Technology. So today he will talk about quantum argument shift method for the universal European algebra. So now, Dr. Ikeda, you may start to talk.
Douglas, thank you for your introduction. Uh, I made a mistake on my title, and the correct title is Constructing Quantum Argument Shift Algebras via Quantized System Operators. But anyway, I'm going to begin my talk. So from the first, I would like to introduce my core topic or core theorem. And simply, if we take some scalar complex matrix square, and and we use some set of operators introduced by these three people, defined on the linear operators defined on the universal enveloping algebra of the general linear D algebra. And just consider some linear combinations of these operators defined by matrix C. Then we obtain some particular operator on the universal enveloping algebra, and our main result is that if we take arbitrary central elements from the universal enveloping algebra, then iterated applications of this particular operator, then we obtain some mutually commutative elements. So fixing an arbitrary scalar matrix, then we obtain some family of mutually commutative elements. And I think you already know, but both. So if G is a Lie algebra, then naturally there are two associated algebras associated to this Lie algebra. One is a symmetric algebra, which is written by SG, and the other one is the universal enveloping algebra, UG. And they are both associative algebra. The symmetric algebra is a commutative algebra. On the other hand, the universal enveloping algebra is generally non-commutative algebra. And from the quantum mechanical point of view, the symmetric algebra corresponds to some classical descriptions of some particular system, and the universal enveloping algebra describes some like quantum aspects of the system. And another point is that the symmetric algebra is recovered from the universal enveloping algebra in this way. So it means that the symmetric algebra is the associated graded Poisson algebra defined by the universal enveloping algebra. And also from these relations, the Poisson bracket on the symmetric algebra is also induced by the structure of the universal enveloping algebra. And the symmetric algebra contains the Lie algebra itself as a linear subspace, and also it is a subalgebra of the smooth functions algebra on the dual space of the Lie algebra. Uh, uh, More precisely, the symmetric algebra is the algebra of polynomial complex value polynomial functions on the dual space of the Lie algebra. And so I explained that the symmetric algebra is Poisson algebra, but also this smooth functions algebra also a sorry, Poisson algebra, and it is uh, uh, determined in the way that the Poisson bracket, which is called Lie Poisson bracket on C infinity G star, is a unique Poisson bracket on this algebra extending the original Lie bracket of the Lie algebra. So now C infinity G star is also Poisson algebra. It means that the dual space of the Lie algebra G is a Poisson manifold. So if we have a Poisson manifold, then we can consider deformation quantization due to contribute and so on. So now we consider deformation quantization of the Poisson manifold G star. So we obtain some star product on this algebra, and the value is usually the formal power series. Here I write this formal parameter by mu. But if we take some correct or appropriate star product, which deforms a Poisson structure of C infinity G star, then the restriction of this star product on the symmetric algebra is contained the polynomial algebra of the symmetric algebra. So it means that it means two things. The one thing is that if we restrict a star product on the symmetric algebra, then the resulting power series in fact terminates. So it's not a form of power series, but finite just polynomial. We obtain polynomial, and also it means that the coefficients belong to the symmetric algebra. So now it makes sense to put this formal parameter equal to 1. Then first we take some product of two elements. Then we have polynomial, and then putting mu equal 1. Then we obtain some particular element of the symmetric algebra. So in this way, we obtain new product on the symmetric algebra, which is also written by this star. Then, in fact, we obtain we obtain another product on the symmetric algebra. In fact, the symmetric algebra with this new product is isomorphic to the universal embedded algebra. So this is another relation of the symmetric algebra and the universal embedded algebra. So the universal embedded algebra is a kind of deformation continuation of the symmetric algebra in this meaning. So now we suppose that the Lie algebra is finite dimensional and take some basis. E1 to ED. Then, so since symmetric algebra is, as I explained, so it's polynomial functions on G star. So in this algebra, we have partial derivatives with respect to these variables, E1 to En. And again, we can consider some linear combination. Then it is a directional derivative along to the direction C from the real space G star. And if we write C bar for the Poisson center of the symmetric algebra, then the classical theorem due to Mishenka and Fomenka says that we obtain Poisson commutative family. So this is the original classical theorem, and our main result is a kind of quantum version of this classical theorem. So in this way, from theorem of Mishenka and Fomenka, we obtain some Poisson, we can generate a Poisson commutative sub-algebra generated by these iterative shifts. And because that SG is a graded algebra defined by UG, Weinberg asked if this this symbolic C is called the argument shift algebra, and this theorem is sometimes referred to as argument shift method because this directional derivative is connected to the idea of shifting some elements of the algebra. So Weinberg asked if this Poisson commutative sub-algebra C can be quantized to a commutative sub-algebra of the universal Mbek algebra in a way that the same relations of this also holds between Shibak C and Shik C. Then a commutative algebra Shik C satisfying this relation is called quantum argument shift algebra. So this proposal is called Weinberg's problem, and for like 20 years it was studied by many mathematicians. For example, Nazarov and Olshansky constructed quantum argument shift algebra using Yangians and twisted Yangians, and also Tarasov used symmetrization mapping from the symmetric algebra to the universal Mbek algebra, and constructed the quantum argument shift algebra. And another prominent way is to use the Feigen-Frankel center, and for regular X, Feigen and his company, and also Rybnikov studied this framework, and also for type A simply real algebras, Patoni Morev and Morev Yakimova studied also and constructed quantum argument shift algebra and studied generators and so on. And our motivation is to quantize not only the algebra Shibaku, but the shift operator itself. So, uh, so to this end, now I want to introduce uh, quantum derivation to construct quantized shift operator. So from now, we should we have to restrict our attention to not general real algebra, but a particular real algebra, general linear real algebra. Then we have the square element of generators, basis element satisfying the commutation relations as uh, like the same way as matrix units. So this is the same commutation relations as D by D matrix units. So we have this kind of standard basis element. And then, as I explained, so there are the square elements, the square numbers of partial derivatives. Then this partial derivative satisfies like trivial conditions, and especially the important one is the Leibniz rule, as you know. So and this partial derivatives can be characterized by these conditions. But since the universal embedding algebra is not commutative, so the same axiom doesn't work. And these Gurevich, Pyatov, and Saponov modify the Leibniz rule, then obtain some well-defined operator. So the square elements of some quantized partial derivatives. So now we have operators on the universal embedding algebra. So let large C be the center of the universal embedding algebra, and as I explained in the beginning, taking numeric matrix and consider linear combination, then we obtain commutative family. So this is the main result, and also we can say that subalgebra generated by these commutative elements is in fact the quantum argument shifter algebra, which Weinberg defined. So to prove it, first we can assume that X is diagonal. And then in this case, Weinberg and Rybnikov characterize the quantum argument shift algebra, and it is in fact the centralizer of some set of finite elements, these elements. So they describe quantum argument shift algebra in a convenient way. And since the quantum argument shift algebra is commutative by definition, so the proof can be carried out by showing that these quantum argument shifts commute with these elements. In fact, so this is the way to prove our main theorem. And the center is described by, for example, there are several ways to describe, but one way is considering matrix composed by basis element which are introduced, and consider some powers and trace. So this gives some uh, independent generator of the center algebra. And we can describe central elements in terms of trace of power of generating matrix. So now it is useful to study quantum derivations of the power matrix power of generating matrix. So uh, this is just remark. So if we modify uh, our quantum derivation operator, uh, 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 then quantum Leibniz rule is also modified uh, 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 to be a homomorphism of algebra. So this is another convenient description. So if we use this uh, notation, then first my first result is quantum derivation can be written in a concise formula, and this can be done just by induction. So from assuming this form and calculate n plus 1 power and using commutation relations and so on, then we obtain some recursive formula with the initial condition, this kind of initial condition, and also recursive relation. And this can be solved, and the solution is just this polynomial. In this way, I obtain this this formula for quantum derivation. And so, and so the inductive step reduces to proving this kind of commutation relations between some of operators, and it can be done by computation. Then, as I explained, so now we can also describe quantum argument shift algebra using our shift quantized shift operators and so considering quantum shifts up to nth order, then we obtain increasing sequence of sub-algebras converging to the quantum argument shift algebra. So by my calculation, the first order can be described by center and this kind of trace c times n power of e. This, center and these elements generate the algebra shape C1. And proceeding this calculation, then I obtain some kind of description using some matrix and so on. Large Pn is some matrix composite binomial coefficients, and taxi is also like very simple operation. So we can describe in terms of this. But in fact, we can say more, and so these generators are redundant, and so M and N can be restricted just close to each other. Because there is a kind of linear dependence between these matrices, and this can be written like follows. And uh, and 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 this year, uh, I uh, I I could I could give a complete proof of this lemma, and some so this lemma have some like property of combinatoric property, and lemma can reduce to this kind of complicated combinatory relation. So I prove this lemma by proving this kind of combinatoric relation. The second, so the first order generator is in this kind of simple form, and now the the second the generator of the second order, if written precisely, then this kind of sequences, and by our main theorem, they are all mutually commutative. So conclusion is that and some remark is that if we consider a representation of another of other real algebras, then we can obtain quantum derivation and quantum argument shift. But in general setting, this naive way doesn't work. So uh, this means that I still don't know uh, how to define appropriately quantum shift operator in other real algebras. So this is the first remark, and the second remark is so maybe it is more promising to generalize this result to the general linear Lie super algebra uh, uh, general linear Lie super algebra, and I'm currently working on it. Thank you very much for your attention.
Okay, okay, okay. Let's thanks Yasushi for his wonderful talk. So, is there any other questions?